We are living in this amazing age of artificial intelligence, right? We've got models like GPT-3 that can write poetry, whip up code, and hold conversations that feel incredibly real. But there's a huge hidden catch, a massive cost that could actually put the brakes on the future of AI.
So let's get right into it. The big problem here is that AI's incredible skills are built on just a staggering amount of energy consumption. It's a massive efficiency problem, and it's really holding back that next big wave of innovation.
Okay, so check this out, because this is where it gets wild. A huge AI model, something like GPT-3, has about 175 billion parameters. Now, your brain has around 86 billion neurons, so, they're in the same ballpark, right? But now look at the energy. Training that AI can burn through millions of kilowatt hours. Your brain, it just sips on about 12 watts. That's less power than a dim light bulb. I mean, that is not just a gap, that's a canyon. It's a mind-boggling difference.
So you gotta ask, right? How on earth is the human brain so ridiculously efficient? What is its secret? Well, it turns out the answer to that question is the key to building the next generation of AI.
What researchers are starting to realize is that the solution is all about mimicking the way our brains actually work. It's not about how many neurons you have, it's all about how you use them.
And here's the absolute key. Your brain is dynamic. When you recognize a friend's face or listen to a song, you're not firing up all 86 billion neurons at once. That would be an insane waste of energy. Instead, your brain is smart. It only activates the small, specialized circuits it needs for that specific job. But that's not how most AI works today. Nope. They do the exact opposite. They light up the entire network for every single calculation, no matter how simple.
And that, right there, brings us to the hero of our story today, dynamic neural networks, or DNNs. These are a whole new class of AI designed to work more like our brains. Instead of having a fixed, rigid structure, they can actually change on the fly, adjusting how they work based on the exact problem they're solving in that moment.
Okay, so how does this actually work? Well, it kind of breaks down into three main flavors, and each one has its own clever trick for being way more efficient.
First up, we've got sample-wise dynamic networks. The idea here is pretty simple. Not every problem is equally hard, right? So this kind of network takes a look at each individual piece of data, what we call a sample, and decides how much brain power to actually use on it. If it's an easy question, it gets a quick, low-energy answer. If it's a tough one, well, it brings in the heavy hitters.
And the analogy for this is just perfect. Imagine you're taking a test. Once you've answered enough questions to know you've locked in an A, are you going to spend another hour sweating over the extra credit? Probably not. You just turn it in. That's what these networks do. They have these early exit points that let them stop working as soon as they're confident they have the right answer.
All right, next up is the second type, spatial-wise networks. This one's all about visual stuff, like images. Instead of painstakingly analyzing every single pixel in a huge photo with the same level of detail, these models learn to focus their computational attention only on the parts that actually matter.
I mean, this is literally how your own eyes work. When you're trying to find a friend in a big crowd, you don't carefully study the patterns on the sidewalk or the clouds in the sky. You scan, you find their face, and you focus right there. These AI models do the exact same thing, saving a ton of energy by just ignoring all the background noise.
And that brings us to our third and final category, temporal-wise dynamic networks. This type is built for data that happens over time, like a video or an audio recording. And the key insight here is that, when you watch a video, a lot of it is kind of repetitive, right? Not much changes from one frame to the next.
Yeah, the best way to think about this is like hitting the fast forward button. You don't watch every single second of a 2-hour movie just to find that one big action scene. You skim through it. That's what these networks do. They pay super close attention when things are happening, but they basically fast forward through all the boring, redundant parts.
Okay, so we've got these three brainy strategies. But what's the bottom line? What do we actually get out of it? Well, it's all about building AI that's way smarter and more efficient, instead of just making it bigger and hungrier for power.
Let's kick things off with the big, flashy number. For the exact same level of accuracy, these dynamic networks can be over 10 times faster. That's a massive leap forward. This is a total game changer, making things that were once way too slow and expensive totally possible. We're talking about doing complex real-time video analysis on your phone or running faster drug discovery simulations, all without needing a giant supercomputer.
And the wins just keep coming. It's not just about raw efficiency. They're also way more adaptive. Just imagine a self-driving car that can pour all its processing power into navigating a crazy intersection, but then chill out and save energy on a long, empty highway. They have a higher capacity, so they can learn more complicated stuff without needing more power. And, this is a big one, they're easier to interpret. Because they focus their attention, we can actually see what parts of the data they're using to make a decision, which is a huge deal for building AI we can actually trust.
Okay, so this all sounds amazing, right? But let's be real, it's not all smooth sailing. This is still a pretty new field of research, and there are some pretty big hurdles that scientists and engineers are still trying to figure out.
Basically, researchers are bumping up against three main hurdles. First, the deep theory of why these dynamic networks learn so well is still kind of being written. Second, actually training them is a real headache because you're mixing simple on or off decisions with all these fine-tuned adjustments. And finally, our current computer chips, like GPUs, were built for those old-school brute force AI models. They're just not optimized for this new, flexible way of thinking yet.
But even with those challenges, the potential here is just undeniable. As the National Science Review puts it, this whole approach offers a really promising fix for the energy crisis that's facing big AI. Pretty much everyone agrees this is the way forward.
And that leaves us with this one big, kind of mind-blowing question. We started this whole thing by comparing AI to the brain in terms of pure efficiency. But as these networks start to think more like a brain, will they also start to gain the capabilities of a brain? Could this be the secret that finally closes that gap between artificial intelligence and, well, us? Only time will tell.